Hello, and welcome back. We have a new chapter, a new section, new everything. We're talking about section 4.1, exponential functions and continuous compounding. The first video, we're going to define exponential functions. Okay, so here's an exponential function. A function grows exponentially if, whenever you increase its input by some amount, the function gets multiplied by some value. So the simplest idea is if we multiply by b, or so if x increases by 1 and our function gets multiplied by some b, some base value, then it's going to look like that. It's going to look like f of x equals b to the x power. So this is fundamentally a different creature from x to the n. Just swapping where the constant and the variable is makes this a very different kind of function. So we're going to have to, when we consider the calculus involved here, it's going to be entirely different from our x squared kind of situation. Okay, so just a quick example to get us in the ballpark. 3 to the x is sometimes called the tripling function, and that's because if x goes up by 1, then the y values get 3 times as big. So just for example, if we take inputs of 2 and 3, and we consider what happens when we put them into this function. Well, okay, so if we take an input of 2, remember we're replacing the exponent with our input. So 3 to the second is 9. And then do the same thing, 3 to the third. This is 3 times 3 times 3. We get 27. Well, all right, our inputs went up by 1. We went from 2 to 3. And our outputs went from 9 to 27. They got multiplied by 3. We can even see that in the outputs themselves. 3 to the third is 3 times 3 times 3. This is 3 times 3. So we're just missing an extra factor of 3 from this one to get from this input to the next one in line. If we plot all of those points together, all those different real numbers, 3 to the sum value, then we get a graph that looks like this. So this is a graph of 3 to the x, for instance. And maybe the most interesting characteristic of which is that as we move to the right, this graph explodes and we get really, really big, bigger than x squared, x cubed, x to the fourth, x to the 50th in the long run. And then as we move to the right, the graph levels out at the horizontal axis. Because we're talking about functions that look like b to the x, then if x is 0, we'd be looking at something that is always b to the 0, and that's just going to be a value of 1. So what is common to these exponential functions of this form, at least, is that they always pass through the intercept 0, 1. And just kind of formalizing some of these notions that we've talked about, here are properties of exponential functions. So basically the good stuff. If we've got b to the x, and let's look for just positive values on b. That's going to mean we're looking at exponential growth. But so what that implies is you can plug in any values of x. It's always continuous, and you're never going to get a number that's 0 or smaller for this output. No matter what exponent you pick, b to that power is going to be a positive number. We've got a horizontal asymptote right at the x-axis. We've got, as we mentioned, the y-intercept is 0, 1. It doesn't cross the x-axis, well, not exactly because of this horizontal asymptote thing, but this certainly helps. So there is no value when we take 0 equals b to the x. If we tried to find an x-intercept, we'd have no real numbers that would make that happen. This says as we move to the left, it bottoms out at 0. This says as we move to the right, the function keeps getting bigger and bigger, goes toward positive infinity. And then the other situation, if we end up with a value of b that's between 0 and 1, that is some kind of fraction for b, then we get the flipped situation. As we move to the left, the graph is headed up pretty steeply. And as we move to the right, it bottoms out instead. So this is a b is between 0 and 1 kind of situation. So if we start with a fraction, then basically we flip this graph sideways. And then finally, the function's increasing if b is greater than 1. And then it's decreasing in this situation when we have this fraction situation. Okay, so that's just a big old data dump. But here's one of my favorite applications of exponential growth, just to kind of see how this plays out. So the average thickness of a piece of paper is about 0.1 millimeters. So it depends on the grade of the paper and whatnot, but let's just stick with that. Okay, so our questions, and there's a few of them. How thick is a piece of paper if you fold it over once? What if you fold it in half twice? What if you fold it in half 3 times? And then we'll formalize that and get an equation that describes what the thickness would be if we fold it in half and we ignore the resistance. So that is a big if. Folding it becomes progressively more and more difficult. It physically resists us doing that. Okay, after how many foldings will it take for the paper to be? 51.2 millimeters, so that's about 2 inches thick. Or your math textbook, more or less. 51.2 looks like a weird number, but we picked it for, for a good reason. Okay, and then finally, how thick is the paper after 50 foldings have gone by? Okay, so remember the part A question was, what happens when we fold it once, what happens when we fold it twice, and 3 times? So if we start with 0.1 millimeters, then folding it once is going to make it twice as thick. We're going to have the 2 layers of paper, one on top of the other. If we fold it again, then we're taking the 2.2 millimeters that was already there, folding it on top of itself, so it's going to double and get 0.4. If we do that again, 0.4 folded on top of itself is 0.8. Okay, so those are the first. Now, we're going to try to generalize this. What would happen if we did this t times? So we looked at a tripling function, 3 to the x earlier on. But instead of tripling this time, what we really want is doubling. And that actually gives us the base for this function. The constant thing that we want to be multiplying by every time is 2. So initially, let's say, okay, maybe it looks like 2 to the t. But that's not quite right, because if we let t be 1, so 1 folding, we get 2 millimeters, but we really want 0.2 millimeters. And if we did t squared, we'd get 4, and what we really want is 0.4. If we did t to the third, we'd get 8. What we really want is 0.8. So basically, what we figure out is that we're off by exactly a 0.1 times 2 to the t. So if we just took 8, 4, and 2 and multiplied them by 0.1, we'd be exactly where we want. So we'll get our final function by doing precisely that. We'll take 2 to the t, and we'll just tack on this multiple of 0.1 in front. Okay. Now, we wanted to get a paper thickness of 51.2 millimeters. And there's 2 choices, basically. We can think of this as, basically, either we're setting t equal to this number, 51.2, or we're setting the f, the output of this function, equal to 51.2. Well, I don't want to fold the paper 51.2 times. That's not what this says. It says I want the thickness to be 51.2. So that's the output of the function. So basically, we're taking f of t and setting it equal to 51.2. So there's our function altogether, written in my typical 2nd grade scrawl. So this is the equation we want to solve, and we can do at least one kind of typical thing. We could divide both sides by 0.1. And if we do that, that's fine, but we end up with sort of a weird situation. This is not a mathematical equation that we can get out of simply by adding, subtracting, multiplying, or dividing, our typical means of getting t by itself. The fact that it's stuck in the exponent there is kind of complicated. So in general, we'll need something new, which we get in the next section, and you will have already seen in a college algebra class. But we'll just note here that we do have a very special power that gets us there. 2 to the 9th happens to be exactly 512. And if you're asking yourself, what would I do if this was something other than a very nice number like 512? And that's a perfectly reasonable question. The answer is we'll need the skills of our next section in order to make this work. But because we picked the numbers the way that we did, we could do this without those special tools, logarithms. And we see that the exponent being 9 would do the trick for us. So t equals 9. And that ought to mean that we, just to put the word conclusion on this, that we'd have to fold the paper 9 times in order to make this happen. Fold it in half 9 times over itself. Okay, so again, we'll take our function, and then we're going to ignore the nature of physics, basically, for the time being. And we're going to try to fold this thing 50 times. So there's all kinds of weaknesses involved in this, but we're simply imagining that we can kind of, maybe instead of folding, you can imagine cutting in half and then stacking on top of itself. Cutting in half and then stacking on top of itself. So we don't lose horizontal component either, like when we would fold from the side. Okay, at any rate, so what this looks like is I want t to be 50, so we want f of 50, and this is 0.1 times 2 to the 50th power. Okay, before I keep going, I'd like you to pause if you're watching this, presumably, and see if you can guess what you think this might be. So you think it would be as thick as a math textbook? Do you think it would be a foot thick? Would it be as tall as a building? What sort of comparison would you have? So I'm going to assume that you've paused now. That's how many millimeters. Now, look at this. So here's thousands, millions, billions, trillions, quadrillions. 112.5 quadrillion millimeters. That's kind of a ridiculously large number. And for comparison, let's note that the mean distance from the Earth to the Sun is 1.52 times 10 to the fourth millimeters, and we came up with 1.12 times 10 to the 14. So about 2/3 of the way to the sun is how tall this stack of paper would be. So obviously that's totally ridiculous physically, but what it does do for us is illustrate how quickly exponential functions grow. Because if we were cutting and stacking this paper and we did it 50 times, this is a ridiculously large number. So the best lesson we can draw from this is that functions that look like 2 to the x, 3 to the x, etc., grow extraordinarily rapidly. Okay, so another piece of this is some reminders about exponential rules. We've already been using these throughout the term, but just a reminder of all the pieces that go into our exponent stuff. So basically, the equality rule says if the bases are the same, then the exponents have to be the same. So if these two things are equal to one another, the only way to make that happen is if x and y are equal. If you multiply two things with the same base, you add their exponents. If you divide two things, you subtract the exponents. And if you raise a power to another power, you multiply those exponents. If you've got two things raised to a power, they can sort of get broken up. And as long as they're being multiplied, note that there's no a plus b to the x running around here, just a times b. So if you've got things getting multiplied to the x, you can raise each of them to the x. And things getting divided raised to some power. You can write them as one to the x and the other to the x getting divided. And just some quick reminders about these things. So we'll make some assumptions that we've got positive exponents that are variables or positives, so we don't have to worry about square roots of negatives and so forth. So the thing that we're after here is this weird expression. So it's a bunch of stuff getting multiplied to the negative 4/3 power. So we can make use of the rule that breaks these things up. We've got negative 4/3 power, we've got 1, 2, 3 terms in there. So we can raise each of them to the negative 4/3. So there's our exponent. And then once we do that, we can start breaking down the components a little bit. So this piece is going to take a moment. So we're probably going to let that stew for a minute. But each of these have exponent rules, exponent things that can get resolved pretty quickly. Negative 3 times negative 4/3 is just 4. And 3/4 times negative 4/3, those are going to cancel out almost perfectly. So at the risk of running out of interesting colors here, we're going to have this whole chunk turn into positive 4. And then we'll have this piece over there. They basically cancel each other out. So we're down to the only way they don't perfectly cancel each other out is that there's still this factor of negative 1 there, which is going to drop it in the bottom. So y to the first if you really want, x to the fourth on top. And then this is a numerical computation, but we can do this without too much trouble. Cube root of 64 says, what do I have to multiply by itself 3 times to get 64? Well, 4 does the trick. And then 4 to the negative 4th power, 4 times 4 times 4 times 4. 16 times 16 is 256. And it's in the denominator because that exponent is negative. Another example using not just simplifying an expression, but trying to solve an equation. We've got 3 to the 3x minus 1 equals 81. And again, we've got logarithms, which we'll make use of in the next section. But here we can actually make some progress just based on what we've got here. 81 happens to be the same thing as 3 to the 4th power. And if we use the equality property, that says that there's basically no way for these two exponents to be equal to one another unless, these equations to be equal unless the exponents are equal to one another. So since it's 3 to the something on one side and 3 to the something on the other side, these things must be equal to one another in order to make this work. So that gives us a much nicer equation to solve, just exponent equals exponent, because their bases were both 3. So then we add 1 to both sides, we divide by 3, and we're home free. So hopefully these are some reminders about our properties of exponents and exponential functions that we've run through in Math 111, college algebra. We'll be back for another video that talks about some of the applications of exponential functions, and I'll talk to you then.